Just some extra problems on conditional expectation and expectation using conditional expectation, covariance, and so now I want to get into something new. That's moment generating function. So with this, we are nearing the end of the syllabus. So once we go over moment generating functions, the moment generating functions is a very useful tool in probability, and we will use this to prove this central theorem of probability, which is called the central limit theorem. Now, I think I mentioned this earlier, that there are two important central theorems in probability, and they are the law of large numbers and the central limit theorem. And in fact, even now, most of the research done is related to these types of proofs. People are still trying to prove different sort of varieties of law of large numbers or different versions of the central limit theorem that you can apply to different situations.
Are we learning the law of large numbers?
Just the statement and something called the weak law of large numbers. The strong law of large numbers, we will not be able to prove it, but I can state it. So this moment generating function in section 7.7, it's called moment. And now when I say moment generating function, I'm just going to write MGF. Moment generating function. The moment generating function, which x such with capital X of t, of a random variable x, is a function, this is a function of t, for all t, given by mx of t is defined as the expected value of e to the tx. So I take my random variable x, I multiply it with t, take e raised to that, and calculate the expected value of that. That's a definition of moment generating function. Why is this so useful? Because you can use, and why is it called moment generating function? Because in a sense it generates moments. If you take the derivative of this and set t equals 0, so that means calculate, you get the first moment. Do all of you remember what I mean by moments? So kth moment of x, I just mentioned it once, kth moment of x is just this. And clearly you see, to calculate variance, I need the second moment of x. It's the second moment of x minus the first moment squared. That's our variance of x. So if you can find an easy way, say if I give you the moment generating function, you can generate all your moments, so it makes calculating mean and variance very easy. Functions because, and here's why. Take the derivative with respect to t. Now, we're going to do something that if you are a mathematician, you would want to see verification of this, and that is can you interchange expectation and the derivative? This is not an obvious thing, but for all the distributions we're going to look at in this class, you can always interchange expectation and derivative. So when you take the derivative inside, if you differentiate this with respect to t, you get capital X e to the tx. So now the derivative of the moment generating function is the expectation of x times e to the tx, expectation of a product of random variables. Now, let me look at this at time t equals 0. So that is at time t equals 0. What happens? You get x at e to the 0. So that's e to the 0 is 1. Just so if you take the first derivative and set t equals 0, you get the first moment. Let's see what happens with the second moment. So we're taking the derivative of tx. We get, taking the derivative inside the expectation, you get x squared e to the tx. Therefore, it is just expected value x. So you can keep doing this, and basically you see that if you take the nth derivative of your moment generating function, you get x to the n e to the tx. So the moment generating function, the nth derivative at t equals 0 is just this number. The nth moment. So this is one way in which the moment generating function is a useful tool, and there are other properties of moment generating functions that make it very useful, and we will get to them eventually. But first, let's calculate the moment generating function for some of our known distributions. So let's calculate the moment generating function for binomial, for Poisson. We'll also do exponential and nominal. And you can do any others that you like. All right, so let's start with calculating moment generating function. Moment generating function for a binomial random variable with parameters n and p. So we're going to come up with a very general formula. Mx of t is the expected value of e to the tx. Let's take the expectation of this. So it's a summation. K goes from 0 to n, e to the tk, times the probability that that's the expectation. And I said the final isn't cumulative, but you need to know these things because the moment generating function will be on the final, and you will need to know this for the to calculate the moment generating function. What is the probability mass function for a binomial random variable? It's n choose k, p to the k, 1 minus p to the n minus k.
Are we allowed to to use the formula sheet for the final or not?
Yes, you are allowed to use a formula sheet for the final. If you already have a formula sheet with the probability mass function, probability density function for the random variable you studied, don't throw it away, just keep adding to it.
Keep adding to it, okay. Is it one page again, or?
My one for last test was 1 page.
Yeah.
I mean, it was already a full page.
Okay, so then you'll memorize some stuff.
Dang it.
I mean, it's a little strange if I, let you guys bring pages and pages.
No,
yeah, and
not
one
pages
page.
and pages, just pages. 2. Just 2. Make life easy. I'm so familiar with my last one. It's like it's laid out nicely, Okay, fine. Formula sheet 2.0 to revamp the whole thing.
That nicely, it would take a whole page.
Well, I don't know. I guess
Hey, mine took a whole page too. It's fine, thank you.
Okay, so, well, it's always good to rewrite formula sheets because then you remember stuff. If you've written a formula sheet more than a month ago, then you should rewrite it. Just as a sort of like refresher course. All right, so let's get simplified formulas for this. And choose k. And we have e to the tk, so that means we have e to the t raised to k, and times p raised to k, so it's e to the t times p raised to k. And then 1 minus p. The reason we're writing it like this is because we have the binomial formula, which says that, and I've used this before too, that's your binomial formula. So this looks like your binomial formula where your b is 1 minus p, your a is e to the t times p. So this is e to the t times p plus 1 minus p. So this is your moment generating function for a binomial random variable. So on the exam, if you need to use the moment generating function for a binomial random variable, you can either rederive it or you could memorize this formula or put that on your formula sheet. Oh yeah, okay, so let's use this formula and see whether we get the right mean and variance. We know that the mean of this is, so first let's calculate the derivative of this. The derivative of this is function of, so your function of t is in here, so n e to the t p is 1 minus p to the n minus 1 times p e to the t. So plug in t equals 0, what do you get? N e to the 0 p plus 1 minus p to n minus 1 p e to the 0. So e to the 0, that's 1. So n p plus 1 minus p to the n minus 1 times p, which is n times p. So you just get 1 to the n minus 1, which is the mean b. So for variance of x, to calculate that, we know this formula, and we can calculate the expected value of x squared, that is your second moment, from the second derivative of your moment generating function. Let's calculate the second derivative. So here you use the product rule, n p b to the n 1 times p e to the t plus n p e to the t n minus 1 times e to the t p plus 1 minus p, the n minus 2, and p e to the t. And so when we evaluate this at 0, what do we get? We get n. When t is 0, you get p plus 1 minus 2, which is 1, so that's just 1 p plus n p n minus 1 becomes 1, and you get another p. Variance of x is going to be np plus n times n minus 1 p squared minus the mean, which is n squared p squared. And you can simplify this to get plus n squared p squared minus n p squared, n squared p squared, and p1 minus, which is our variance. Okay, so once you have your moment generating function, you can just take the derivatives and evaluate them at 0 to get your moments. And you can use that to calculate mean and variance. So you could have a problem like, yeah.
I noticed that for the original moment generating function, before we do any derivatives, if we evaluate for t of 0, we're getting a value of 1. Is that something that's consistent through moment generating functions?
So, I mean, consistent in the sense, oh, you mean, yeah, you mean like, will mx of 0 always be 1? Yeah.
Okay.
Another question. Does this have any meaning if we evaluate it somewhere other than t equals 0?
It doesn't give us anything useful.
Okay.
The reason why we look at it as a function of t is for a different purpose. It's not for the moments. It's eventually to prove our central limit theorem. Okay. So yeah. So the reason we take it, I mean, you would say that why? So we think of it as a function of t because we're going to need this later on. I mean, this is something like, have you guys done things like Laplace transforms? This is basically a Laplace transform. Okay? And Laplace transforms are an easier version of, like, if you take a higher level probability class, you will study something called characteristic functions. They have something very similar in form, except you have an I here. The I as in the complex number I. Okay? And you calculate the expectation e to the itx. And they call it a characteristic function because it characterizes a distribution. That is, every distribution has a unique characteristic function. Now, it turns out that every distribution also has a unique moment generating function. The only problem is sometimes this may not exist. When you try to compute this expectation, say you integrate e to the tx, but the density function is such that this is not a finite number. I mean, this expectation is not finite. So you can have a problem, like moment generating function may not be defined for certain random variables, okay, for some t's at least. So that's why they talk about characteristic functions where they have I here, which makes it well-defined for a function. But for simple problems, the moment generating function is well-defined, and when it is well-defined, it uniquely defines the distribution. And that's the important idea for moment generating function. So if you take any kind of distribution, it looks very different from another distribution, but something tells you they might be the same. Calculate the moment generating function for both. If you get the same value, they have to be the same distribution. Okay? So that is why this is a very important tool. All right. But as to whether the value of the moment generating function at other points has some other meaning, I don't think so. It's only at 0 that the derivatives give you the moments. But then if you are familiar with, so that's why it's called moment generating function, because if you expand mx of t, use a Taylor series expansion. What is the Taylor series expansion of this thing? It's that's a moment generating function, right? So basically what you end up with is 1 plus the first moment times t, plus the second moment times t squared of the distribution, plus the third moment of this cubed distribution. So that's why we call it the moment generating function. In a Taylor series expansion, you would end up with 1. The coefficient of t would be your first moment. The coefficient of t squared would be a second moment. The coefficient of t cubed is the third moment. And you see, if you differentiate this once, this term goes away, this becomes 1, this becomes 2t, okay? And you set t equals 0, this is just 1, so you just get this moment. All these terms have t, so they become 0. That's why you end up with just the first moment. All right, so many ways in which you can see the first moment comes up, but in terms of with which value of t it relates to, it's only to 0.
Wait, so t is 0, right?
No, this is the Taylor series expansion
Yeah, but
about
then
t equals 0.
for the last line, when you put in like 0 for t?
Right, when I say I would differentiate this, and if I differentiate this side, and then set t equals 0, then I get, say I
after
this
differentiating,
once.
gotcha.
Yeah, after I differentiate, set it equal to 0, I get the first moment. If I differentiate the right-hand side twice, this term disappears, that also disappears, because after differentiating this twice, it disappears. This term just becomes 1. And the others will have t in them. So when you set t equals 0, all those terms disappear. You're just left with the coefficient of this, which is the moment.